I welcome each one of you to this video lecture. That is Chemistry, Introduction to General Chemistry 1 with the code Chem 101 or Chem 121. So in this video, we'll look at electronic configuration. And as you are watching this video, I encourage each one of you to join our channel, Mwezi TV channel, for more information on chemistry, physics, mathematics, biology, and even accounts. Okay, so we are starting on our topic, electronic configuration. To begin with, I would wish to explain what electronic configuration is. So electronic configuration simply shows the distribution of electrons, okay, how electrons are being distributed. Okay, so in most cases when people hear the word electronic configuration, they simply think as if it's simply a single thing. But I want to inform you that this one comprises of 5 different types. So we have 5 different types of electronic configuration. And the first one is, it is SPDF, electronic configuration. The next one we have is the number system. So this is the number system electronic configuration. The third one we have is the condensed. So this is the condensed system or the condensed electronic configuration. So the other one we have is the orbital system or the orbital electronic configuration. Finally, we have what we call the partial orbital electronic configuration. So this is what is involved in on electronic configuration. When you just hear of electronic configuration, you should think it in these lines. Are they talking about the SPDF electronic configuration, or the number system, or it could be the condensed electronic configuration, the orbital system, or the partial orbital electronic configuration? So this means that you have to be extra careful when you are answering the questions on electronic configuration, because they exist in this complexity. So you have to know what is to do at each stage of this. So the fact that we are dealing with electronic configuration, it means that we can't ignore the periodic table, because we'll be using the elements from the periodic table. So I have to give the insights before I go in details on electronic configuration. So I want to highlight some items on the periodic table. So what I'm about to draw here is the model of the periodic table. It's not a real periodic table, but it is the model of the periodic table. So it exists in this form. Okay, so this is how the periodic table looks like. So we have elements in this block, and we have to note that the elements found in this block, or this block itself, is known as the S block. Okay, and the elements found in this particular block is, or the block itself is the P block. Then this block here is known as the D block. Finally, we have what we call the F block. So these initials, this S simply denotes sharp. Then we also have this P there, we also have D, we also have this F fine, so they all mean something there. So we have this periodic table, and it's divided actually in what we call groups and periods. So when we talk of groups, we simply mean these vertical columns. Then when we talk of periods, these are horizontal rows. So for instance, this period here is known as, or these elements found here, they are known as alkyl metals. Then in this group too, they are known as alkyl metals. So throughout up to the end of the periodic table, we have what we call the periods and groups. But my main concern is simply you to understand that, for example, here we have magnesium. So that magnesium I have just picked, it has what we call a mass number and a proton number. So when we talk of the mass number, this is simply the combination of proton and neutrons. Then this one, this is the total number of protons in the nucleus of an atom. So in as much as we'll be dealing with electronic configuration, we'll be considering what we call the proton number. But in the actual sense, we are not using the protons, but we are using the electrons. Now, why are we picking 12 when it is a proton number? The reason is simply that the protons in the neutral atom is equivalent to the number of electrons. So if we happen to pick 12, we know that even if it's the number of protons, it's exactly the same number of electrons. So we'll be using this smaller number to demonstrate on the electronic configuration. So I can run this model, and you can do justice to also concentrate on this topic because it is a topic on its own. So as I started earlier on to explain on the SPDF, let me make mention that these letters, they simply denote the names of the orbitals or the place where electrons are being distributed. So we have the S orbital, we also have a p orbital, we have a d orbital and the f orbital. So that particular s orbital simply allows or accommodates only 2 electrons. So only 2 electrons are being accommodated. In the p orbital, the maximum number you can distribute is 6. In the d orbital, the maximum number is 10. Then in the f orbital, the maximum number you can distribute is 14. And you have to note that electrons are being paired. So if we happen to pair these electrons, you simply have just an orbital. Why? Because that orbital accommodates a pair of electrons. If you have 6 electrons, it means you simply need 3 orbitals, because at the end of everything, you need to pair those electrons. So if you have 10 electrons, it means on D block, you simply make sure that you have 5 orbitals. Then on the F part, you indicate 7, because when you pair or divide by 2, you have a 7. Okay. So now, how do we pair those before we start demonstrating on the electronic configuration? These electrons, you can't just pair them like that, whereby they point in the same direction, because by so doing, you are actually violating the law we call Pauli's exclusion principle, which states that when you are feeding those electrons, you make sure that the other spin of the electron points up like that, while the other one should point down. So you should make sure that when you are feeding the electrons, you obey the principle of Pauli's exclusion. Okay, so how do we start? Just going on the periodic table, it's very challenging to deal with electronic configuration, but there is a format scientists came up with, which can help us to actually come up with electronic configuration without further problems. And what is that particular format? Okay. So don't forget we have also F orbital, which accommodates 14 electrons. So I'll write, this is simply something you have to know. Okay. So I'll write 1s up to 8s. So I have 1s, 2s, 3s, 4s, 5s, 6s, 7s. Finally, I'll end on 8s. Okay. So this one is simply telling us that this is the first shell. Then this one is specifying the type of an orbital, which is s. Then on top I'll put an exponent at 2, showing that the electrons that can be accommodated in this orbital, they are 2. So throughout I'll put the power 2, or the exponents 2. And this simply denotes the number of electrons. So I'll come, okay, on P. I'll ignore the first part as well as the last part, meaning I'll remain with 2. When I ignore the last part, I'll remain with 7. So I'm on P now. So this is the type of an orbital. Sorry, this is supposed to be 3. 4P, 5P, 6P. Even this one is 7P. And as we know, this one accommodates 6 electrons, so I'll put the power 6 throughout, the power 6, 6, the power 6, and even that side I'll put 6. When I come to a d orbital, I'll make sure that I again ignore this part, even the other part, meaning I will begin from 3, d up to 6d. So I'll have 4d, 5d, and 6d. So d, we said it accommodates 10 electrons, so I'll put the power 10, even there 10, even there 10, even on 6d it will have the power 10. Okay. Then finally, let me go to the f orbital. I will do the same, I will ignore this part, and even the last part, so I'll have 4f. The last one will be 5f. So f orbital accommodates 14 number of electrons. Okay, so what am I going to do after this? We should also consider, apart from Pauli's exclusion principle, which is telling us to make sure that these spin points different directions, we also have another principle that is known as Aufbau's principle. So this Aufbau's principle states that when you are feeding in these electrons in these orbitals, you start from the lower energy level before you go to the higher energy level. So what we mean is, you start from this one, regarded to be the lower energy level, starting point, then I'll come to this part, I'll come to that part, that part, that part, this part. Finally, I'll have that part. So it means that when you are using this, you can start from this one. The next one will be this one. The next one, you can't go to 3s2 because this one is lower than 3s2. So you come back to this tail, then you go to 2p6, 3s2, then you can't again go to 4s2, but you come back to this. So how is this helping us? So I'll simply take 2 examples on SPEF and the number system, then it will be our end. So I have 2 examples, or I want to write 2 examples. So example 1. It is right. The SPDF system and the number system of magnesium. This is the chemical symbol for magnesium, and sodium. Okay, so this is our example. So don't forget our question. Our question is requesting us to write the SPDF system as well as the number system of magnesium as well as the sodium element. Okay, so before I wrap this, I want to collect data there. So my data is, so I have the first thing to be magnesium, the second thing is sodium. Okay, then I have to write the condensed, the number system and the SPDF system for the two. Okay, so I'll wrap this so that I write the solution. Okay, so coming to magnesium, here I want to write the SPDF system of magnesium. As I was introducing, I said we are normally using, or we are always using, the atomic number. So the atomic number of magnesium is 12. So how do I write the SPDF? The SPDF for magnesium, we use this format I have just written there. So I'll be picking these items until these exponents add up to 12. So I'll begin from 1s2, because this is our first item. From there, we'll come to 2s2. From there, we'll not go to this one. We'll obey the law of outbound. So we'll come to 2p6. So in as much as we are writing these items, we should be very attentive that when we add these numbers, they are finally adding to 12. So we are simply remaining with two items there, or two numbers. So from 2p6, we write 3s2. So by so doing, you discover that 2 plus 2 is 4, plus 6, 10, plus 2 is 12. So this is simply what we call SPDF electronic configuration of magnesium. Now there is the remaining part on a number system. So for the number system, you actually start from the SPDF, then you proceed. So solving that, I'll simply proceed from this solution. Okay. So what you do after you write the SPDF, for you to proceed to number system, you simply arrange this like this. You consider these coefficients. So we have 1s2, then we have two similar coefficients, that's 2h2. So we'll group those. So we have 2s2, 2p6. Then we also have 3 as the coefficient on its own. So this is 3s2. And we are simply adding the coefficients, the powers. So here you simply have 2. Here we are saying 2 plus 6 is 8. Then here you simply have 2. So finally our number system will be, 2, 8, 2. Then you are done. So coming to this one, I will not solve this one. I will require every one of you to solve this and post on the same channel, Mwezi TV. I want you to solve the SPDF for sodium and the number system for sodium. So many of you may wonder why we have Na. So this is natrium in Latin. Okay. So I thank you for watching this video as we are waiting for you to upload the answers for this question as well as subscribing to the same TV channel. Thank you. This is Mutinta Andrew.